Okay, 10:30, we should start. So the assignment was due last night. I will post solutions before the end of the week, and there's going to be an assignment 5, which also has 5 problems, but they're all pretty straightforward. I think it's the easiest of the assignments. I'm going to post most of it today, at least 3/5 of it today, and the rest of it by the weekend. And I think I'm going to make it due a week from Monday. So you have what day is it today? Wednesday. So you have 12 days to work on it. If there are any questions about any of that, let me know or send me an email. We have 2 more lectures today and Monday. And Monday's the last lecture. So we're going to get through the rest of chapter 12. This is the theorem we proved last time, but I kind of rushed at the end and I didn't realize that I skipped a step. I corrected that on Piazza, but for the sake of those who are going to be watching these videos in the distant future, let me just quickly review the gap and what I should have said. So I have to restate the theorem anyway. So this is Cartan's existence theorem for closed geodesics. If we have a compact Riemannian manifold and a non-trivial free homotopy class of closed paths, of course, this only can exist if the manifold is not simply connected, because these free homotopy classes are conjugacy classes within the fundamental group. So if we choose one of these, then there exists a closed geodesic of this manifold in this free homotopy class. So in other words, for any closed loop which is not freely homotopic to a constant, which is not null homotopic, then you can find a closed geodesic freely homotopic to it, right? All you need is compactness. So the small gap that I inadvertently skipped over was the following. At some point in the proof, we had epsilon was the length of gamma minus d over 2n plus 1, and we chose a natural number k such that L of gamma k was less than d plus epsilon. Let me write it this way: L of gamma k minus d was less than epsilon, and the distance from gamma k of t to gamma naught of t was less than epsilon for all t in 0, 1. This was the uniform convergence. And then when I finished the step of the proof, I never used this, right? So obviously there was a gap. So we showed that that there exists some j naught from 1 up to n such that the length of gamma j naught k plus 2 epsilon is less than the length of gamma j naught. And then I said this contradicts that gamma j naught is minimizing from gamma of t j naught minus 1 to gamma of t j naught. But I didn't clarify why this says is minimizing, because this length, if I add 2 epsilon to this length, and it's less than this, then certainly this is less than this. But that's not the contradiction, because this doesn't have the same endpoints, right? So here's gamma, the restriction of gamma to gamma of t j naught minus 1 and gamma of t j naught. And where's my chalk? Did I forget I forgot my colored chalk. We're gonna have a black and white lecture today. Gamma k, these points are not the same. They don't have to be the same. Okay, so why is there a contradiction? Well, I know that there exists a minimizing geodesic joining these points. These are minimizing geodesics. And because the distance between gamma k of t and gamma naught of t is less than epsilon, and these points are the same as gamma naught, right? That's how we did this. We took the gamma naught at these partition points and we replaced it by gamma, the geodesic. So these points are the same. There's a minimizing geodesic from here to here and here to here, and these distances are less than epsilon. because the distance between any of these corresponding pairs of points for any t is less than epsilon. So therefore, if I went from here to here, and then here, and then here, this length is less than the length of that plus the length, well, it's equal to the length of this plus this plus this, and each of these is less than epsilon, and that's where I use it. And now I'm done because now I have a curve joining these points, right? A curve from here to here, piecewise smooth curve, whose length is less than this, but this one was minimizing. So there's the contradiction. Okay, so now that gap is cleared up, and then the next thing we did was all correct. So I want to make some remarks about this proof, about this theorem, before we move on. So here's a picture. Take the torus. You notice I didn't say what the metric was there. There was no condition on curvature in this theorem. That's why this is a very powerful theorem. So there are lots of metrics you can put on a torus. The usual one is the flat metric, when you think of the torus as the quotient of R2 by a lattice. But you can also think of the torus, for example, as a surface of revolution in R3, and then it's not flat. It has some other curvature. But in any case, we know what the fundamental group of the torus is, right? It has two generators. Here's a loop that's not null homotopic. And so, well, let me make a more complicated one. I wish I had my colors today. So this is not null homotopic. Cartan's theorem says that it's homotopic, freely homotopic to some geodesic. And in this picture where I've drawn the torus with the induced metric from R3 as a surface of revolution, this guy you can show as a geodesic. And similarly, if you take a generator for the other element of if you take a representative for the other generator of the fundamental group, it's a curve that goes around like that. You can see again that you can homotope to this, which is a geodesic. This one's actually minimizing. You can even homotope it to the outer equator there of the donut. That's also geodesic. That one's not minimizing. Anyway, so you can see this theorem in action here. The first remark, two remarks. Compactness is essential for this theorem, and we used it in two places. One is where we used to show that this D was positive. This D was the infimum of the lengths of all the curves in the class script L. And that we used compactness for, and then we used it again later somewhere. But here's an example where M is not compact, where you do have a non-trivial free homotopy class that doesn't have a closed geodesic. So if you take a curve like this, it's again a surface of revolution, and you revolve it around the z-axis, then this is a Riemannian manifold. This is even complete. I mean, I didn't tell you what the graph of this function is, but you can choose a function and revolve it around the z-axis to make this complete. But there and pi1 is not trivial. In fact, you can see that pi1 is just z. This thing is deformation retractive. There's a deformation retractive this manifold onto the circle, so it has the same fundamental group as the circle. But you can show that if you take something in the non-trivial homotopy class, this does not. There's no closed geodesic in this homotopy class because the let's see, why is that? Now I'm confused.
Yeah, so it looks like you have closed geodesics, but they're not minimizing.
Yeah, that's right. That's right. They're not minimizing. Yeah, I'm copying this remark from the textbook. There are geodesics. There are closed geodesics here, but they're not minimizing. So what did I say in the statement of the theorem? Did I say it was minimizing, right? I guess I didn't say that. the way we constructed,
But is that example really complete?
well, it depends how you
Like-
choose the function. Yeah, you can.
It's kind of missing a point, isn't it?
But the point is, it takes infinite amount of time to get to that missing point. Yeah. So there exists a minimizing in the theorem. I should have said minimizing, and you saw how we proved it. We did get the closed geodesic we obtained did have length d, which was the smallest length of any closed path in that homotopy class. So here there exists closed geodesics, but you can make them with total length as small as you want. So there exists closed geodesics in the non-trivial class with arbitrarily small length. So this is something that you should learn in classical curves and surfaces, that if you have a surface of revolution, the geodesics are the meridians and the equators. And then the second remark, this theorem is actually true even if pi1 is 0, is trivial, but the proof is much harder. And I don't know where to tell you to look for the proof, but there are references in the Carmos book. So what do I say this theorem is true? If you have a compact Riemannian manifold, there will exist a non-constant minimizing closed geodesic. Okay, but of course it will be homotopic to the trivial loop, and we know that for the spheres, right? The equators are closed geodesics, and they're minimized. While they're minimizing, no, let's see. What do I want to say? What does it even mean to say minimizing it? So minimizing is the wrong thing to say here. Yeah,
zero
smallest
length.
Yeah,
Geodesics, like you have points, right?
Yeah, so this means there exists a closed geodesic of M in the class of L with minimal length. That's what I meant, right? Because it's a closed geodesic, right? So it's going from a point to itself. So of course it can't be minimizing between its endpoints. I mean that its length is the smallest length of any element of L. That's how we constructed it, right? By taking a minimizing sequence. So then what do I mean here?
So could you please restate you said the theorem was true even if the fundamental group was trivial.
Yeah, I'm trying to think. That's
So
what I'm trying to figure out.
So L has no elements, like you know.
L has no L. Yeah, that's right. So what it means is that there exists non-constant closed geodesics. So let me just state it. Yeah, that's right. So if pi1 of M is 1, it's still true that there exist non-constant closed geodesics. But the proof is harder, right? That's the and here too, right? There are closed geodesics here, but they don't satisfy this property of having minimal length among all elements in that pre-homotopy class. Okay. So anyway, these were just meant to be asides, right? I didn't want to dwell on this. What we want to do is prove Priceman's theorem, and I think we can today. I misstated Priceman's theorem last time when I said what a non-trivial subgroup meant. Non-trivial just meant it's not the trivial group. It could be the whole thing. So Priceman's theorem so MG compact and sectional curvature negative, then any non-trivial subgroup, non-trivial abelian subgroup H of pi1 is infinite cyclic. And here, non-trivial means H is not the trivial subgroup, but it could be the whole thing. This is allowed. I misspoke. So I think I said I excluded that as well, but I shouldn't have. And I don't remember if I wrote down abelian. Okay, so any non-trivial abelian subgroup of the fundamental group, if you have a compact manifold with negative curvature, must be infinite cyclic. And you can turn this around to get, this gives you a topological obstruction to existence of negative curvature metrics. So if you have a compact manifold and you say, you know, can this manifold possibly have a metric with strictly negative sectional curvature? Well, you look at the fundamental group, and if it doesn't satisfy this property that every abelian non-trivial subgroup is infinite cyclic, then it can't. So we're going to prove this today. So we need, before we can prove this, we need some preliminary results. And the goal, the idea is, remember, the fundamental group is isomorphic to the group of deck transformations on the universal cover. And I even told you exactly how that isomorphism works. We didn't go through the details. I will remind you because it's going to be relevant today. I don't know why I'm holding a pen. So what are these preliminary results? Let's make a definition. So let's let mg be Riemannian and m tilde g tilde the universal cover. Right, this is simply connected, and the projection, the covering map from m tilde to m is a local isometry. Before I make the definition, so this is our compact manifold. A lot of these preliminary results are not going to need m to be compact, but this is the universal cover. So pi is a covering map at local isometry, and the group of deck transformations, is isomorphic to the fundamental group of M. And I explained this last time, but I'll explain it again when we need it in about half an hour. But the important point here is that every F in A of M tilde that is not the identity is an isometry with no fixed points. Okay, the fact that it's an isometry is immediate from the fact that the definition of the what does it mean to be in here? This is the diffeomorphisms such that pi compose F equals pi, that it just permutes the sheets of the covering around. And from the definition of G tilde, it follows that that's an isometry. And again, from this isomorphism here, it's exactly, or the fact that it permutes not from this isomorphism, but the fact that it permutes the sheets is what tells you that if you have any fixed point at all, it has to be the identity. Anyway, these are facts from algebraic topology that I just stated. So here's the first definition. Let F be an isometry with no fixed points. For example, a non-trivial element of this group of deck transformations. but all we're going to use in this definition here is that it's an isometry with no fixed points. Then this is called, F is called a translation if it leaves invariant some geodesic gamma tilde of M tilde, G tilde. So what do I mean by leaves invariant a geodesic? That is, if we look at the image of this geodesic, remember, a geodesic is a map from some interval into the manifold. The image is some subset of this manifold that F maps this image onto itself. Okay, it doesn't have to fix the points on the geodesic. In fact, it can't, because it has no fixed points, but it kind of slides the geodesic onto itself. And we say F is a translation along gamma tilde, along gamma tilde. And there may be more than one such. As long as there exists some geodesic which is left invariant by this isometry F, then we call it a translation along gamma. And of course, here's an example. If I take Rn with the Euclidean metric. So here I stated it for the universal cover, right? But it's really for any Riemannian manifold, you can, well, I guess, yes, for a simply connected Riemannian manifold, you can make this definition. This is the universal cover. This is the universal cover of the flat torus. Okay, so it certainly fits in there. And if we take an ordinary translation from elementary school, f of x equals x plus v is a translation for v not equal to 0, right? Translation along a geodesic. And which geodesic was infinitely many here. It's the geodesics with direction vector v. So gamma tilde of t is p plus tv. This is the line through p in Rn in the v direction. We know those are geodesics for the Euclidean metric, and this translation is preserves, right? It moves these geodesics onto themselves. But in the examples where we're going to need this notion today, we're going to be working with curvature negative, and we're going to show, one of the preliminary results we're going to show is that if there is such a thing, there's only one. And that's somehow showing that negative, one second, the negative curvature is more rigid. It's a lot more rigid than this flat case. Yeah, question.
In your definition of translation, are you assuming the geodesic is finite, like it's defined on some closed interval?
No, the geodesic doesn't have to be finite. So the domain of gamma tilde is some, you can just take the maximal interval, right? It's okay. Some open interval, doesn't have to be finite. Yeah. In fact, it is, I do mean the maximal domain. Okay, so here's the first preliminary result. We're going to use this at least 2 or 3 times today and Monday. So maybe I should call it, well, I'll just call it proposition. So let M G be compact. Let M tilde G tilde be the universal cover with the covering metric, and let alpha be an element of this deck transformation group with alpha not equal to the identity. Then alpha is a translation. Okay, so we already know that every element of the deck transformation group that's not the identity is an isometry with no fixed points. And this definition is about isometries with no fixed points. But what we're showing here is that if the manifold is compact, then all of these things, the original manifold, whose cover is M tilde, was compact, then all of these things are translations. Okay. So I'm going to call this the translation proposition, because when I refer to it later today and on Monday, I want you to remember which one it is. So in order to do this proof, we have to recall how this isomorphism works. The isomorphism pi1, and here I have to pick a base point. The deck transformations with pi1, we choose, it's not canonical, right? Even when we pick a base point for our fundamental group, we have to pick a point p tilde lying above p. So choose p tilde in M tilde such that pi of p tilde is p. And given a class G in pi1 of M at p, non-trivial, let's let alpha p tilde G be the deck transformation corresponding to this class G under this isomorphism. This isomorphism, and let me just remind you how that works, because it's going to be relevant for this proof, and I want to keep it on the board until the very end. So I went over this last class. This is defined by alpha p tilde G. If I apply to some point q tilde, it's beta tilde q tilde of 1, where sigma tilde is a path in M tilde from q tilde to p tilde. Then sigma is pi composed sigma tilde is a path in M from q to p. And then beta is you first travel along sigma, then G, then sigma inverse. This is a loop in M at Q, because sigma takes us from Q to P, G loops us around at P, and then sigma inverse takes us back to Q. Beta tilde Q tilde is the lift of beta to M tilde starting at Q tilde. Right? Whenever we have a covering map, if we have any path downstairs and we choose a point above the initial point of our path, there's a unique lift. This doesn't have to be a loop. This doesn't have to close up on itself again. And then therefore alpha p tilde G of Q tilde is the final point of beta tilde Q tilde. And I'm parameterizing them all on 0 to 1. So I didn't prove that this is the isomorphism, right? This is just a fact. And then also, if Q tilde equals P tilde, we can take sigma tilde sigma to be constant loops, constant paths. And that means we can take beta to be G, and therefore alpha P tilde G applied to P tilde is just you lift G starting at P tilde and you take the final point. Okay, I'm going to need this also. All right, with that reminder, now let's prove this proposition. So we have to find, given an element in this group of deck transformations, we're going to use the compactness, we're going to use Cartan's existence theorem. We have to find a geodesic gamma tilde upstairs, which is left invariant by that element. Okay, so we need to find, so given alpha p tilde g in A of m tilde, we need to find not the identity. We need to find a geodesic gamma tilde of m tilde left invariant by this map. Okay, and this being not the identity, that's equivalent to this is not the trivial class. Okay, this is a group isomorphism, right? So the identity goes to the identity. So if we're not the identity, then this G is homotopically non-trivial. So G is homotopically non-trivial, hence determines a non-trivial free homotopy class script L, because remember, it's not the identity, so it lies in a conjugacy class, unique conjugacy class, which is not the conjugacy class of the trivial loop, and therefore that's a non-trivial. The conjugacy classes in the fundamental group are the free homotopy classes. Since M is compact, Cartan's existence theorem, which I just reviewed, says that there exists a closed geodesic gamma in M, freely homotopic to G. And that means it's in this class. Okay, let's draw a picture. I should have really brought my colors today. This is gamma that's given to us by Cartan's theorem. Let's choose a point Q on the image of gamma. Okay. And let sigma be a path from P to Q, from Q to P. So this P is this one, right? We fix to understand this isomorphism. Remember, I had to pick a base point for my fundamental group. That's my P, and then I even had to pick a P tilde above it to get this isomorphism. So P is somewhere, and sigma goes from Q to P. Then gamma is homotopic to sigma followed by G followed by sigma inverse. This is a loop at Q. And this is because gamma is freely homotopic to G. So when I say here, this is homotopic this is as loops at Q. So I didn't go over this, but when I said that free homotopy classes correspond to conjugacy classes in the fundamental group, essentially what that means is that if I took two curves which are freely homotopic to each other, this is G is a loop at P, and then I join a point on one to a point on the other, because these are freely homotopic, by going first, which way did I do it? First here, then around G, and then back, I get a loop at Q, and this is homotopic as loops at Q to gamma. So you can check this. This is, I'm not going to write it again. This is essentially the content of when I say a free homotopy class is a conjugacy class in the fundamental group. Okay. So now let's let sigma inverse tilde at P tilde be the unique lift of sigma inverse, which goes from P to Q, starting at P tilde. Okay, so P tilde lies above this point in the covering space, and sigma inverse goes inverse goes from P to Q, so I can lift it. Let me draw another picture. P tilde sigma inverse tilde at P tilde has some endpoint. Let Q tilde be the endpoint. So it's equal to sigma inverse tilde P tilde of 1. Okay, and that of course lies above Q because sigma tilde is a lift of sigma inverse. So pi of Q tilde is Q, since sigma inverse tilde P tilde is a lift of sigma inverse. Okay. So now I have this point here. I can now lift, gamma goes through Q, and Q tilde is a lift of Q. So I can now lift that path to a point gamma tilde, to a curve gamma tilde. Let gamma tilde be the unique lift of gamma starting at Q tilde. So really I should put a Q tilde. Is that what I have? I do have a Q tilde here. Let's put a Q tilde. And there's no reason for this one to be closed. Okay, but pi compose gamma tilde Q tilde equals gamma. This tells us that gamma tilde Q tilde is a geodesic on M tilde, because pi is a local isometry, and being a geodesic is a local property. That picture is good enough. So we want to show, this is the geodesic I want. We'll show that this map alpha G P tilde leaves invariant this geodesic. And I'm just going to call this gamma tilde so I can avoid putting all of this notation. Right, then we'll be done, because that's what we want to show. We want to find, we found a geodesic. We want to show that this is invariant under the action of this element. And it's going to follow by the way we made all our choices. So here's the first claim. Oh, here's the main claim. This map, this element that we care about, is the same as alpha Q tilde gamma. Remember, we needed a point down here which lies above some point in M, and we needed a loop at the pi of this, right? So pi of gamma, pi of Q tilde is Q, and gamma is a loop at Q. So these are both as elements of A of M tilde. So these are maps, isometries from M tilde to M tilde. Okay, so once we show that these are the same, it's going to be easy from this description to show that it leaves gamma tilde invariant. So let's just make sure we understand here. G is a loop at P, and gamma is a loop at Q. Okay. So proof of the claim. Well, gamma is homotopic as a loop at Q to sigma inverse G sigma, that should still be on the board here, right here. Okay. So since these are both homotopic loops, that means their lifts starting at Q tilde have the same endpoints. This is part of, the verification that that isomorphism that's thankfully still on the board is independent of all those choices I made, right? Whenever you have two loops that are at a point that are homotopic, and you take their lifts to the universal cover and you look at the endpoint, the lifts might not be the same, but the endpoints will be the same. And these lifts are, well, when I lift gamma to start a Q tilde, it's what I call gamma tilde. And the other one is sigma inverse G sigma lift at Q tilde. And this is what I called beta Q tilde on that board on the left, which is still there. So I'm going to keep this here. Okay. So beta tilde Q tilde of 1 is the same as gamma tilde of 1. They have the same endpoint. That's what I just said over there. But what's this? Well, what's this one? This is alpha P tilde G of Q tilde. That's the definition of this map. And this one is alpha P tilde G of Q tilde. That's this guy. Sorry, what am I doing? Q tilde gamma, right? If these points are the same here, how do I do this? I just take that loop and lift it at that point and take the endpoint. So I've got them, the P's are replaced by Q tildes there, and the G is replaced by a gamma. Okay, so I have this equality. So hence, if I look at alpha P tilde G inverse compose alpha gamma Q tilde, this is an element of the group of deck transformations because it's a group, and this leaves Q tilde fixed because of this condition. So the only elements in the group of deck transformations that have any fixed points is the identity. This means that alpha P tilde G inverse compose alpha Q tilde gamma is the identity. And that means that they're equal. So alpha P tilde G equals alpha Q tilde gamma, and the claim is proved. And now it follows easily. So now it remains to show gamma tilde is invariant under this guy, which we just now showed is easier to write like this. So suppose gamma tilde of S is a point on the image of gamma tilde. Let me draw the picture. So this is Q tilde. Maybe gamma tilde of S is here. Remember, how do we calculate where this is sent by this? So alpha Q tilde gamma of gamma tilde of S, I showed these are the same, right? So I got to show that a point gamma tilde of S gets sent by this to some gamma tilde of something else, somewhere else on gamma tilde. Okay, well, how am I going to do this? I pick a path. The description is still here. right? I pick a path in M tilde from the point that I want to map to this reference point, and my reference point is Q tilde. So I can take this as my sigma tilde. Take sigma tilde to be gamma tilde inverse, not gamma tilde restricted to 0s inverse from gamma tilde s to Q tilde. And that means that sigma, which is pi composed sigma tilde, is going to be gamma restricted to 0s inverse from gamma of s. I don't need to write that out. And then therefore the beta that we get this beta, this recipe for computing this map, we first choose a path from the point where we want to apply the map to this point down here. This is gamma tilde of s for us, and this is Q tilde. We chose the path, which we could just take part of gamma tilde, and then we can construct this thing. And then what we need to do is lift this at that point and take the final point, right? So what does this map do? I follow gamma in the opposite direction, but I'm on gamma, and then I'm still on gamma here, and then I'm still on gamma. These are all portions of gamma, okay? So this is on the image of gamma. This curve lies on the image of gamma. So beta tilde gamma tilde s, which is the lift. Where am I? The lift of beta to gamma tilde of s lies on the image of gamma tilde, and this is by the uniqueness of liftings. Maybe I'm not putting enough details here, but
Question.
yep.
So I don't understand the statement that beta is on the image of gamma, because beta, contains gamma, right? Oh, like what are these stars?
These are concatenations of paths. That's why I'm using stars.
Okay.
It's not composition, right? So we follow. Let me draw the picture here on Q. Gamma is a loop at Q. This is gamma at S. So beta is you go from here to here, then you go all the way around, and then you go here again. It's basically equal to gamma.
Oh, okay. Okay.
Right? It's equal to gamma. So beta equals gamma.
Like sigma was different before. Sigma was connecting two different points.
Yeah,
but now
and
you're saying the points are on the curve.
They are.
Okay.
Yeah, they are. It is connecting two different points, but now the point is because my initial point is on this gamma tilde, I can connect them with gamma tilde itself.
I see.
Yeah.
So this is the translation.
This is the translation.
Yeah.
So this,
Okay.
that's the end of the proof. Okay.
Yeah.
So we just proved that if you have a compact Riemannian manifold, then any element of the group of deck transformations of its universal cover, which is not the identity element, is a translation. It does leave some geodesic invariant. And all we used there was compactness. We got to use the negative curvature in Priceman's theorem is going to be used now. So, okay, let's see how much of this I can do. Okay. So now, very soon, we're going to specialize to negative curvature, but we need another digression on geodesic triangles. And this basically is assignment 4, question 5 that you just handed in last night. So let's let M G be Riemannian. A geodesic triangle T is a set in M, is a subset formed by 3 minimizing geodesics. As follows. It's easier just to write down, to draw the picture. And I explained on the assignment exactly what that looks like. So I have 3 points A, B, C in M. And then between each pair, I have a minimizing geodesic. And then this will have some length. Let's call this length capital B, this length capital A, and this length capital C. Okay, that's a geodesic triangle. And then here's this lemma, which you proved on this assignment. If your Riemannian manifold is complete, simply connected, and has non-positive curvature, then a squared plus b squared minus 2ab cosine gamma is less than or equal to c squared. So this angle is gamma, this angle is beta, and this angle is alpha. Those are the angles between the tangent vectors at the initial points. And alpha plus beta plus gamma is less than or equal to pi. Okay, so you did this on the homework. I will post the solutions either tomorrow or the next day. And moreover, this is part that we didn't put on the assignment. These inequalities are all strict if K is always negative, if this inequality is strict. Okay, so I didn't ask you to prove this on the homework, and only for one reason. It's the same proof that you did for the inequality, the non-strict inequality case. You use Rauch's theorem, but when we stated Rauch's theorem, we stated it with a non-strict inequality, right? It said that if you had some K tilde was greater than or equal to K, then the norm of J tilde was less than or equal to the norm of J. Right? It gives you a comparison on the size of the Jacobi field based on a comparison on the curvature. And what I should have said at the time, and I didn't because Dokarma didn't even mention it, even though he uses it now, was that in the Rauch comparison theorem, if you have a strict inequality as your hypothesis on the curvatures, then the conclusion is a strict inequality on the Jacobi fields. So this is because Rauch comparison K tilde greater than K implies J tilde less than J. So you can check this. If you just go through all the proof of Rauch comparison and see wherever we had this inequality, we had this with a equal to, greater than or equal to, we wanted to show this with a less than or equal to. If you make them all, if you make this strict, then this becomes strict. So so I am going to use this, the fact that when K is negative, these inequalities are strict. I'm going to use it in a few minutes. The other remark I should say about this, I won't write it down. You can also have a non-negative version of this as well, and a negative version. The only issue is if it's not, you know, why is this nice? Because when K is non-positive, the Cartan-Hadamard theorem tells us if it's complete and non-positively curved and simply connected, we know it's diffeomorphic to Rn. So we know that these geodesic triangles can be as large as we want. There's going to exist, in fact, a unique minimizing geodesic between any 2 points in this case. But if the curvature is non-positive, non-negative, if the inequality is the other way, you can only assure yourself that you'll have geodesic triangles if all the lengths are sufficiently small, if you're contained inside some totally normal neighborhood or geodesically convex neighborhood of one of the points. So I'm not going to write that on the board because I'm not going to use it. But what I wanted to say is that this theorem about geodesic triangles, if you change this to non-negative, then these change. And if this is strict positive, then these become strict positive, but only if the geodesic triangles are sufficiently small to make sense, right? That's the only issue that goes wrong there. And you may have seen this sort of when you hear about Euclidean geometry, right? In a negatively curved space, the sum of the angles of a triangle is less than 180 degrees, and in a positively curved space, the sum of the angles of a triangle is bigger than 180 degrees. Okay. So now we're ready for Priceman's theorem. I'm going to break it up into 3 claims. And I think I can do 2 of them today and the third one on Monday. And luckily, we don't need any of this stuff anymore. This was just to prove that translation proposition. And this geodesic triangle we're going to need in claim 2, I believe. So we're not going to need it again on Monday, if I remember correctly, I hope. Okay, so let MG, this is the 3rd time I'm writing this, be compact, negatively curved if H is a subgroup, a abelian subgroup, and non-trivial, then H is infinite cyclic. Of course, that's not really a restriction, right? Because the trivial subgroup is abelian, but of course it can't be infinite cyclic because it's a finite group. Okay, so here's the proof. As I said, a series of claims. He breaks them up into lemmas, which actually is probably a smarter thing to do, because if we do get to some other related results on Monday, I don't know if we'll have time. One of the ingredients in the proof of those related results will be one of these subclaims, but it's okay. So let pi be the covering map from the universal cover to M, and suppose F is a translation along some geodesic, along a geodesic gamma tilde. So remember, what does this mean? In particular, F is an isometry with no fixed points, because the definition of a translation was take an isometry with no fixed points, then it's called a translation along gamma tilde if gamma tilde is a geodesic and its image is preserved by F. Then gamma tilde is the unique geodesic left invariant by F. Okay, so the crucial ingredient here is that K is negative. Because in the example I gave you of translations in Rn, there were infinitely many geodesics that were preserved, whose images were preserved by any of these translations. But that, of
There's
course,
a
has zero
little
curvature.
typo.
Yep. What's the typo?
In the statement of the theorem, it looks like you're writing H equals 1. You mean not equals?
Yeah.
That's what it looks like.
Yeah. I do that a lot. Sorry, not equals. Okay. So this is saying that we already know from the translation proposition that anything in A of M tilde, anything in the deck transformations that's not the identity is a translation. And this claim is not even about just things in the group of deck transformations. It just says if you have a translation along a geodesic and the curvature of the thing that whose universal cover you're looking at is negative, so therefore this is also negative, then there's only one such geodesic. So proof of claim 1, suppose there exists gamma 1 tilde, gamma 2 tilde geodesics on M tilde not equal. These are maximal geodesics, right? So they both have their maximal domain, such that F of the image of gamma tilde 1 is equal to is contained in, I guess it'll be equal because it's a bijection, gamma tilde 1 and F of gamma tilde 2. This, we need to find a contradiction. We need to obtain a contradiction So first, suppose that that these two images were not disjoint. Okay? In fact, I'll show that this can't happen. The images are disjoint. Then there exists a point P, P, let's call it P, in this intersection. If it's not empty, there's something in there. And then let Q be equal to F of P. This has to also be in there, because each of those sets is preserved by F. So if I take something which is in both of those sets, its image under F will be in both of those sets. And Q is not equal to P, since F has no fixed points. So I have these two distinct points, and they're both on, I guess I shouldn't put any arrows here. They're both on the image of gamma 1 tilde and on the image of gamma 2 tilde. So I can look at the portion of gamma 1 tilde from P to Q and the portion of gamma 2 tilde from P to Q. And therefore, I have two distinct geodesics. We get two distinct geodesics joining P to Q. But this contradicts the Cartan-Hadamard theorem. Cartan-Hadamard, which because this Cartan-Hadamard, all you need is non-positive curvature. We have negative curvature. So K tilde is negative. And that tells us that the exponential map is a diffeomorphism. Okay, so this says, so any two points are joined by a unique geodesic. Okay, this is not always true on even on a complete Riemannian manifold, but if it's non-positively curved and simply connected, then the Cartan-Hadamard theorem applies. And then we know that any two points are joined by unique geodesic, and it's minimizing. So why is that? Because let's say I have, if I have two geodesics from P to Q, those geodesics will have initial point P and some initial velocity. I can normalize them, right? That means if I take the initial velocity, call this V, and the V1, and the initial velocity of gamma 2, I call it V2, that means that Q is XP of LV1, and it's equal to XP of LV2, where L is the distance from P to Q. And this contradicts the fact that this is a bijection. Okay, the only way this can happen is if V1 and V2 are unit vectors, V1 has to equal V2. So then it's gamma 1 equals gamma 2. Okay, so when the exponential map is a diffeomorphism onto Rn, in the case of complete, simply connected, and non-positively curved, then any two points, not only are they joined by a minimizing geodesic, but that's unique. So we got a contradiction. We're not done yet with claim 1. We got a contradiction to this, right? If this intersection was not empty, then we get a contradiction. So the image of gamma 1 tilde intersect the image of gamma 2 tilde is empty. Let's let P1 tilde be an image of gamma 1 tilde. I don't know, there I wasn't putting tildes, here I am, I don't know why. And P2 be in the image of gamma 2 tilde. So P1 tilde is not equal to P2 tilde, because we just proved that their intersection is empty. And let's let gamma 3 tilde be the unique minimizing geodesic joining P1 tilde to P2 tilde. So here's the picture. P1 tilde, P2 tilde. This guy is on gamma 1 tilde, and this is going to be F of P1 tilde. It's still on gamma 1 tilde. And here's gamma 2 tilde, and this is F of gamma 2 tilde. What did I write? F of P2 tilde. And this one is gamma 3 tilde. And minimizing geodesic from P1 tilde to P2 tilde. Then I can also look at F composed gamma 3 tilde. And because F is an isometry, that's going to be a geodesic. And of course, it takes F of P1 tilde to F of P2 tilde. So this is a geodesic quadrilateral. Let's put some angles in this picture. Let's call this alpha, beta. I want, let's call this one alpha prime. So this one is going to be pi minus alpha prime. And let's call this one beta prime. So this is pi minus beta prime. Okay. So let alpha, beta, pi minus alpha prime, pi minus beta prime be the interior angles as shown. Okay, since F is an isometry, alpha prime equals alpha and beta prime equals beta, because isometries will preserve angles, right? So if I look at this geodesic and this point, under F, it gets sent to this point and this geodesic, and the angle here is going to be equal to the angle here. The same thing there. So hence, the sum of the interior angles of this geodesic quadrilateral are, well, I have alpha plus pi minus alpha plus beta plus pi minus beta, and that's 2 pi. Okay. Now, I really wish I had the colors today. This is the worst time to forget the colors. I'm going to redraw this picture. I want to create two geodesic triangles. So there's my geodesic quadrilateral. I'm going to draw two pictures because there's two possibilities for what could happen. Okay. I'm going to join one vertex to the other by a unique minimizing geodesic. Okay. It could look like this, or it might look like this. We don't know. Okay. There's no reason it has to stay in between. So make two geodesic triangles, T1, T2, by joining P1 tilde to F of P2 tilde by minimizing geodesic, which exists and is unique because it's a Cartan-Hadamard manifold. And so it might end up, I mean, obviously it could also go the other way, but this is the same as this one, right? The point is the velocity vector of the final point of this geodesic, if I started from here coming out, it might be between these two, or it's either between these two or on the other side. So in either case, the sum of the two angles of the triangles which meet at that vertex P2 F of P2 tilde is at least the angle of the quadrilateral. So what do I mean? In this case, if it really comes in like this, then definitely this angle plus this angle is equal to this angle. Okay. In this case, I have one of them here, and here's another one. Now, when I add them, it's greater than the angle for the, sorry, what have I done here? Which are my two triangles? This is one of them.
You need to draw it from the curve to the kind of vertical.
From the curve to this one. There you go. Thank you. So in both cases, it's from yeah, it's from the curve I made to the other sides, right? So in this case, they add up to the angle of the quadrilateral, and in this case, one of them is already the angle of the quadrilateral, and the other one is more, right? So when I now add up the angles of the two geodesic triangles, so let's look at the sum of the angles of T1 plus the sum of the angles of T2, well, that's going to be at least the sum of the angles of the quadrilateral, which is 2 pi, right? Because the corresponding pairs here add up to at least the angle of the quadrilateral. So hence, at least one of T1, T2 has the sum over the angles is at least pi. Because if they were both less than pi, this wouldn't happen. But that's a contradiction to the lemma from assignment for question 5 that we just reviewed, because we're in the negative curvature case. So this is strictly negative, right? This should be less than pi. Okay, so that proves claim 1. I'm probably going to have to stop here.
Question.
Yep.
So you drew the two cases at the terminating end of the kind of diagonal, but don't you also have those cases at the initial end?
Yeah, that's right.
at
I mean, you're right. Yeah, I shouldn't have drawn it like this. The point is, you're right. It doesn't have to start like this. It could have also been like that. But I only looked at this side, right? I'm saying no matter how the geodesic from here to here looks, right, its initial velocity might start out in between or not in between. Those are the two cases. You just have to look here. But you're
Okay.
right. This phenomenon can happen at any of the 4 vertices, right?
And so the definition of angle, I mean, is it directed angle? I mean, can you get negative angles? Like, how are you defining it?
The angle for us is between 0 and pi. So it's the acute angle between the two tangent lines. Is that okay?
Yeah, I'm just, you have to be careful when you do these like visual proofs.
Yeah, that's true. But I will let you guys worry about the details. I've got 6 minutes. Oh, I can do claim 2 as well, and then we'll start from there on Monday. I will repeat the statement of the theorem a 4th time, and I'll repeat claims 1 and 2 and remind you that we proved them. So suppose G from M tilde to M tilde is an isometry without fixed points. Which commutes with a translation F along a geodesic gamma. Okay, so F is a translation along gamma tilde. G is some other isometry without fixed points, and it commutes with F. Then we claim that G is also a translation along gamma tilde. Then G is also a translation along gamma tilde. This one is easy. So if I look at where does F compose G send gamma tilde? Well, that's F of G of the image of G compose gamma tilde, right? Because F and G are both bijections, right? So F compose G of the image of gamma tilde is F of the image of G compose gamma tilde. And this is a geodesic. And this is equal to, because FG equals GF, they commute, that's the hypothesis, that's equal to G compose F of the image of gamma tilde. And that is equal to G of F of the image of gamma tilde. And that's equal to G of the image of gamma tilde. And that's because F is a translation along gamma tilde. And this is just the image of G compose gamma tilde. So if F and G commute and F preserves the image of gamma tilde, then F also preserves the image of G compose gamma tilde. But then by claim number one, we must have G composed gamma tilde equals gamma tilde, right? Because there's a geodesic which is left invariant by F. And in claim number one, we proved using the negative curvature assumption that there's only one. So this has to be gamma tilde. So G is a translation along, along gamma tilde. So that's another way to write the condition of being a translation along a geodesic. It means that if we post compose the geodesic with that isometry, we get the same geodesic again. And this proves claim 2. Okay, so this is probably where I should stop because there's no way I can get much farther in 2 minutes. So on Monday, I will restate Preissmann's theorem again. I'll state these 2 claims that we've proved. There's one more claim, which will probably take 15 minutes. That's the sort of interesting group theory bit. And then when we finish the proof, I'm going to talk about a very similar result that you can get using the same kind of ideas. That shouldn't take more than half an hour. And then we'll see if we have time to do Bayer's theorem or not. Probably not. That uses some more sophisticated group theory, normal solvable subgroups and things like that, which I could just tell you about, but it'll probably be a good place to sort of call it quits. So we might not need the whole 80 minutes on Monday. We might just need like 50 or 60. Okay, any questions?